Okay, on this video we are going to solve an Euler Cauchy differential equation, but it's not longer homogeneous. So we have a q of x. So that means that we have to find the particular solution. Alright, now the method that we are going to use is parameter variation now. Parameter variation is a method that works with variable coefficients, so that is why we can use it. We cannot use undetermined coefficients because that method only works for constant coefficient differential equations. So let me remark that here. The only method to find particular solution is parameter variation. Please keep in mind that because it's the only method we can use. Okay, so the procedure is actually finding first the homogeneous and then finding the particular solution. Okay, so let's find the homogeneous differential equation. So the homogeneous differential equation is x squared second derivative minus 3x first derivative plus 3y equal to 0. Now the characteristic equation is going to be m squared plus b minus a minus 3 minus 1m plus 3 equal to 0. So this becomes m squared minus 4m plus 3 equal to 0. So that means two numbers in which the multiplication is 3 and the addition is minus 4. I think it's going to be n minus 1 and n minus 3. Alright, yes. So my first root is going to be 1 and my second root is going to be 3. So my first root, my first solution is x and my second solution is x to the power 3. Now, the homogeneous solution then it is going to be c1x plus c2x to the power 3. Okay, we got the homogeneous solution. Now, what we have to find is the particular solution. For that, we are going to use parameter variation. So in the parameter variation, the particular solution is going to be w1 of x times y1 plus w2 of x times y2. Alright? Now, to find w1 of x and w2 of x, we need to calculate w1 of x is going to be the integral of delta 1 over delta differential of x, and w2 of x is going to be integral of delta 2 over delta differential of x. Alright? But what are those deltas? The deltas are the determinants. So I'm going to erase this because I'm going to need it. Okay, now the deltas are like this. The first delta is y1, y2, y1 prime, and y2 prime. What are those solutions? Well, the solutions that we just calculated are of the homogeneous solution. Okay, so let's calculate this. So y1 is equal to x, and the second solution is x to the power of 3. Now, some students actually write here c1 and c2 from the homogeneous solution. Don't do that. You can write it, but in the end it doesn't matter. What we care is about the solutions, alright? Okay, derivative here is 1 and here is 3x squared. So the multiplication of this is going to be 3x to the power of 3 minus x to the power of 3. So this is the solution. This is just 2x to the power of 3. So that is my delta. Okay. Next is delta 1. Delta 1 is going to be very similar determinant, but here you will replace 0 and q of x here, y2 and y2 prime. So this is going to be, but you have to replace here q of x. Now, here is a problem that many students have. You will replace this as the q of x, but that is not the q of x, because this method of parameter variation assumes that your first coefficient must be 1. So we don't have that in the Euler Cauchy differential equation. Alright? So what you have to do is to divide the differential equation by x squared. So that is going to be second derivative minus 3x over x squared first derivative plus 3 over x squared y equal to 2x to the power 4 exponential of x divided by x squared. And what happens that this is the true q of x. So x to the power 4 divided by x squared is going to be 2x squared exponential of x. Now this is the true q of x for the formula, alright? For the formula. Again, we develop the parameter variation assuming that this coefficient is equal to 1. If you do not do that, then your formulas is not going to work. Alright, so, this is q of x. So let's replace the values. So here is 0, the y2 is x to the power of 3, 3x squared, and here my q of x, which is this, 2x squared exponential of x. So delta 1 is equal to, this times this is 0, I don't care. Now this times this is going to be minus 2x to the power of 5 exponential of x squared, and x to the power of 3. Alright, so that is delta 1. Okay, and now let's calculate delta 2. Delta 2 is very similar. So very similar to this, but now you replace the second column. So you will have y1 and y1 prime here, and then here you will have 0 and q of x. So this is going to be y1 is equal to x and 1, and here 0, and here the 2x squared exponential of x. Alright? Okay, so my delta 2 is going to be just this times this, and this is 0, is going to be 2x to the power of 3 exponential of x. Okay, so now let's calculate w1 of x and w2 of x. w1 of x is going to be the integral of delta 1 over delta differential of x. Integral of delta 1 is minus 2x to the power of 5 exponential of x divided by delta 2x to the power of 3 differential of x. Okay, so the result of this is going to be 2 and 2 cancels, the minus goes outside, integral of x squared exponential of x differential of x. Okay, what we have to do is integration by parts 2 times here. Okay, anyway, let's do it. So this is u and this is differential of v. So u is equal to x squared, so differential of u is equal to 2x differential of x. And v is the integral because it's an exponential, is the same exponential. Okay, so that is the integration by parts. Okay, so w1 of x is equal to minus u times v x squared exponential of x minus the integral of v differential of u exponential of x. Differential of u is 2x differential of x. Okay, so this is equal to minus x squared exponential of x minus 2, these 2 goes outside, integral of x exponential of x differential of x. And we need again integration by parts. So u, this is u, sorry, we have another color. This is u and this is differential of v. So differential of u is just differential of x, and v is exponential of x again. Okay, so this is going to be minus this times this. Okay, let's do minus x squared exponential of x, and this times this plus 2 what? U times v x exponential of x minus integral of v differential of u, integral of the exponential of differential of x. Now this becomes exponential of x. Okay, so my w1 of x is going to be minus x squared exponential of x plus 2x exponential of x minus 2 exponential of x. Remember that this 2 multiplies this and this. Okay, we calculate w1 of x. Okay, I may not have enough space, but let's write. Let's skip some steps. Now, W2 of x is going to be the integral of delta 2 over delta differential of x. Integral of delta 2 is going to be 2x squared, x to the power of 3, sorry, exponential of x divided by 2x to the power of 3 differential of x. Now, this one was easy. W2 of x, this and this cancels, fortunately for us. Integral of the exponential of x is just exponential of x. Okay, now let's write the particular solution. Okay, the particular solution then is W1 of x, this big number. I can actually factorize the exponential. Minus x squared plus 2x minus 2 exponential of x. W1 of x times my first solution, and my first solution is just times x, and then plus W2 of x exponential of x times the second solution, and the second solution is x to the power of 3. We can actually reduce that. It's going to be, this is going to be x to the power minus x to the power of 3. So this and this actually cancel with this, and this is going to be just 2x squared minus 2x exponential of x. Now I hope you can see why this and this cancels. Alright, so that is the particular solution. Now what is the general solution? The general solution is just the homogeneous plus the particular. I'm going to write it here. I hope you can see it. So my general solution is going to be C1x plus C2x to the power 3 plus your particular solution 2x squared minus 2x exponential of x. We can actually factorize the 2 here, 2. And this is the methodology to find the particular solution. Again, on Euler Cauchy differential equations, the only method that you can use is this parameter variation, and you have to make sure that this is equal to 1. So your Q of x is going to be different for the formulas. Okay. With this, we have finished the theory, and the next videos will cover the applications.